Welcome to Open Source Options. Today I want to show you how we can take a digital elevation model like this and simulate water flow across the landscape very easily without doing any pre-processing on our DEM. So let's go ahead and get started. Before we get all the way into this, I want to let you know that there are 3 courses coming to opensourceoptions.com. You can go in there, you can register, there'll be a private portal, and on that private portal you'll have opportunities to start discussions and to access free courses. It's not quite ready yet, but in the next couple of weeks it's going to be there. All right, let's jump into the tutorial now. So I have a digital elevation model open here. It's a 1 meter spatial resolution, LiDAR-derived DEM. For this example, we're really going to just take a very, very small portion of this so that we can ensure the computation goes quickly. So the first thing I'm going to do, switch to the latest panel, and I'm going to extract a portion of this or a portion of this raster. So I'll click by extent. I'm going to just draw on the map canvas to do this, and I'm going to select a very, very small portion of this raster. So I'm talking something like right here, these 2 small drainages that come down. I'm just going to draw a rectangle around those. Excuse me, and select that. And then after I click this, I'm going to make sure this is a small enough size. I want the dimensions to be less than 1,000 pixels in each direction for this demonstration so that it goes quickly. Okay, and I'm going to save this to a file, keep all the defaults here, and save this to a file. And I'm going to just call this demo flow DEM. And let's go ahead and run that. Run really quickly. You can see our small DEM we have there. And now let's just open up the properties here. And we can see that it is indeed small, 400 pixels in width and 700 in height, which should give us a nice small area to run this model. Okay, so there is our DEM. Now before we can run this, and I guess I should show you this, I'm going to close out my processing toolbox. You'll need to open the processing toolbox. You can open it from the toolbar here. You can go to processing and toolbox. And now you'll need to have your GRASS tools installed. If you don't have them installed and don't know how to do it, go check out my video on installing QGIS. I show you how to do this really simply. Once you have this open, you want to open up the GRASS raster tools. The tool we're going to use for this is r.sim.water. But before we can simulate the water flow, we first need to get the x and y slope derivatives. And we can get that with the r.slope.aspect tool. So I'm going to open this one up. And I'm going to input my elevation, my demo flow DEM. I'm going to change this to % so that I get a unitless measurement out of this. And I want to make sure that the type of output is set to fcell, which gives me a floating point value. Those are the 3 things I need to set up there. Now, the slope aspect tool has a whole lot of outputs. We don't need all of them for this. So I'm going to skip a lot of these. I'm going to skip the slope output. I'm going to skip aspect. I'm going to skip both the profile and the tangential curvatures. I'm going to keep the first order partial derivatives, dx and dy, which are these next 2 outputs. I'm going to save those to files. I'm going to save this as dx, and I'll save the next one here. I'll save to a file. I'll save this as dy, and then I'm going to skip the remaining outputs. Okay, so make sure you're saving first order partial derivative dx and first order partial derivative dy, and then I'll click run. Now when I run this, those are going to get added to the map. You can see I have dy added there, and I have dx added there, just like that. Okay. Now that I have those, I'm ready to go in and simulate the water runoff. So let's go open this rsim water, and we'll go through the inputs here. So the first thing we need is an input elevation, for which I'll use the demo flow. I need to specify my x derivatives, which is dx, and my y derivatives, which is dy. Those are my three main inputs. I can input those three and leave the defaults and I'll be okay. I'm going to walk you through what these defaults are just so you know in case you want to expand upon this. This first one is the rainfall rate in millimeters per hour. You have two ways to specify this. One is a constant value that'll be applied equally across your modeling domain, across your raster. The other is to input a raster map that has the same characteristics, so same number of pixels, same extent, same cell width as your DEM. And you can specify a spatially variable rainfall rate in millimeters per hour, so each pixel has its own value. We're going to leave this, I'm actually going to drop this down to like 25. Which if we're using imperial units is about 1 inch per hour. The next is infiltration rate in millimeters per hour. So we're just going to leave this at 0, so there's really no infiltration happening. You can pull once again a constant value, or you can upload a value that is spatially variable based on soil or land cover or a combination of the two. The next is Manning's N, which specifies the roughness of the surface, and it has implications for how quickly water flows. We're going to leave the default at 0.1. Again, you can change the constant value, or you can add a raster map that has spatially variable Manning's N values. Those are the primary input variables that are going to affect this. Next, we have some constants that affect water diffusion and thresholds and weighting factors. We're not going to get into those. You can read the documentation. Those are important for your application. Okay, now let's get on to the outputs. These final two outputs are not important. They're optional, and I just get better model consistency when I do not use these. So I'm just going to skip both these last two outputs, the output walkers and the sampling points. And I'm going to save water depth, water discharge, and simulation error to files. Now note the units here because these units don't appear in the file names unless you include them. We have water depth in meters, discharge in meters cubed per second, and simulation error in meters. Let's go ahead and save this to a file. I'm just going to call this D for depth and save. Discharge, save the file, will be Q, and error, we're going to save the file simply as E. And now I'm going to click Run. And you're going to see why I have such a small raster for this. This could take a while to run. I'm not sure exactly how long it will take. Generally, it seems to take about 20 minutes for a raster of this size, but it can also vary. It's going to vary based on the specific terrain you're using, and also based on the size of the raster, and also based on your computer's capabilities and if it's set up for multi-threading or not. I'm going to pause this while this runs, and we'll come back and take a look at the outputs. All right, our simulation has finished. Let's go ahead and close out of this. That took just about 30 minutes. So you're 28 minutes, 59 seconds, even for this very small raster. So you can see how this might take a long time to run through a landscape. You're going to see how useful these results can be. So here we have the output results. Let's just take a look at these individually, turn off the error and the depth. So here we're simply looking at discharge, which is in cubic meters per second. You can see we get up to a high value of 10, which seems pretty high for this landscape. Part of the reason for that, though, is we had no infiltration rate. And so none of this water is infiltrating into the ground, it's all running off, which can explain that. You can look in here and you could see how we get these discharges for different areas, and it makes it easy to pick out some of these stream channels. You'll also notice how in some of these areas, it's pretty easy to identify where there should be some culverts probably as we're running into this road here. But you can see how without needing to run filling a DEM or flow directions or a flow accumulation, we can see what the hydrology looks like for this area. We can also take a look at what the depths, water depths might look like from the storm. So you can see we get a maximum of 2 meters in some locations, which looks like they are up in this area. Probably have some holes that are filled in from the rainwater, and values a little lower here. Also, for a value tool, just to take a look at this, go over to the value tool, turn off our dy dx. We can see our depths here. It's a little wider, are about a ½ meter deep, which probably makes sense for storm that's coming down these stream channels. And also keep in mind that with this context, we don't have the downstream context available, so that could influence things as well. You can see how easy it is to pick out these channels. We can look up at these depths here. We can see these holes are getting filled in around 1.5 meters deep. And you can just see the overall effect and the overall water depth on the landscape that results from a rainstorm and how that can define and give insight into the hydrology. All right, that's what I have for this tutorial. Go give it a try. Try out the R flow simulation tool. See how it works for your study area. And don't forget to check out open source options for those free courses and discussion forums that are coming soon.